In the previous lecture, we have started to discuss the thermodynamic behavior of an ideal Bose gas. In fact, as I have told you in the first lecture, that we will divide this subject in three parts for your convenience. The first part has been already discussed, and you have seen that in first part we have only derived the basic equations for dealing the thermodynamic behavior of the ideal Bose gas in different temperature conditions. Actually, from today we are going to discuss the thermodynamic behavior of ideal Bose gas. And as I have told you earlier, that we will divide this lecture further now in two parts. In two temperature conditions, we will discuss the thermodynamic behavior, because the thermodynamic behavior or the value of different thermodynamical quantities of the ideal Bose gas is temperature dependent. And you have seen that while discussing the problem on Bose-Einstein gas, or you can simply say Bose gas, the critical temperature plays a vital role. And so our discussion will be limited in two conditions. First of all, we will see how this thermodynamical variable varies with temperature, particularly when temperature is less than critical temperature. And after that, we will see that the same property of the ideal Bose gas varies with temperature when temperature is greater than critical temperature. So in this lecture, we are going to deal with the problem of thermodynamic behavior of ideal gas under the condition that the temperature of the gas is less than the critical temperature Tc. Okay? And for this discussion, you will definitely need the basic results which we have actually derived in the first part of this lecture. So for your convenience, I have here mentioned all those previous results which we have discussed in the first lecture on this subject, and these results will be actually needed for our further discussion. So let us see what we have learnt in the previous lecture. You have learnt that actually in case of Bose gas, the gaseous system may be assumed to be distributed in two quantum states. The lowest energy quantum state is called actually ground state, you know, and this is actually the state of zero energy, and the another state you call it excited state, and this is a state where energy of the particles of the Bose gas is not equal to zero. So actually the gaseous system is distributed in these two phases, that is in ground state and in excited state. Okay. We have considered that in ground state the number of particles present is n0, and that in the excited state it is Ne. And the total number of particles in this system was n, and that n is simply equal to n0 plus Ne. Okay. Now we have calculated that what will be actually the value of this Ne. This is number of particles of Bose gas in excited state. And as you can see that this Ne is just equivalent to n minus n0, and that we have calculated in the first part of the lecture. This is equal to V over lambda cube times G3 by 2 of A. Actually here V is actually the geometrical volume in which this Bose gas is taken, and lambda, you know, this is given by this much. This is a square root of h square by 2 pi mkt, and this is called actually the de Broglie wavelength. Okay, this is called de Broglie wavelength. And this function g of 3 by 2 of a, how it is defined? We have learnt in the previous lecture that this gn of a is equal to 1 over gamma n integral 0 to infinity epsilon n to the power minus 1 d epsilon divided by a to the power minus 1 e epsilon minus 1, and this is actually equal to a plus a square by 2 to the power n plus a cube by 3 to the power n, and so on. Okay, actually here in this equation a1, this n is equal to 3 by 2, n is equal to 3 by 2. And so you can evaluate what will be the value of the function g 3 by 2 of a, and a as you can see we will take the value of a in which is actually different in different temperature condition. When a is maximum, then its value is equal to 1, as we have learnt in the previous lecture. Okay, and similarly we have also obtained the expression for the total energy of the gas, and you have seen earlier that this U, which is actually the total energy of this Bose gas, this is given as 3 by 2 kT times V over lambda cube G 5 by 2 of A. Okay, and similarly as you can see that this G 5 by 2 of A can be evaluated from this result, and here this n is equal to 5 by 2. Okay, and we can see that this gamma n is actually gamma function. Okay, these are the two important. Apart from these two results, we have also learned extra two results, which you can see it here, that this Ne is also given like this. Ne equal to, when you will substitute the value of lambda and you express the function g in terms of the Riemann zeta function, then this Ne is given as 2 pi m kt over h bar square whole to the power 3 by 2 times V zeta 3 by 2. You have seen that this zeta 3 by 2, this is a Riemann zeta function, and its value was 2.612. Okay, and the total number of particles, this is given by 2 pi m k Tc divided by h square to the power 3 by 2 V into zeta 3 by 2. Actually, when you will take T equal to Tc, then almost all particles are in the excited state. So we simply consider that when T is equal to Tc or greater than even Tc, then N is almost equal to, Ne is almost equal to N. So substituting simply Tc instead of T in this equation A3, you can get N equal to this much. Okay. Now, actually the behavior of this Bose gas at a temperature less than critical temperature, we have already discussed in the earlier lectures on Bose-Einstein condensation. You know, when temperature of Bose gas is less than critical temperature, then a very famous macroscopic phenomenon takes place, which is called actually Bose-Einstein condensation. In fact, in this phenomenon, almost all particles of the Bose gas are found in the ground state, in the same quantum state of lowest energy, and that is called Bose-Einstein condensation. So definitely, if you are talking about the temperature which is less than Tc, definitely Bose-Einstein condensation will take place. And you have discussed this Bose-Einstein condensation in very detail in the previous lecture. Okay. So something which I am going to talk I have already dealt in the previous lecture. So definitely you have an idea of this. So let us see this equation A3 and this equation A4. If you will divide this equation A3 by this A4, what will be the result? You can see this will be Ne over N, okay? And except this T in equation A3 and Tc in equation A4, all other quantities are common in both of the equations. So when you will divide this Ne by N, then all quantities will cancel out, only there will be T remaining in equation A3 and Tc in equation A4. So you can see that this ratio of Ne over N, this is simply equal to T over Tc whole to the power 3 by 2, okay, whole to the power 3 by 2. And so this Ne can be written as this is N times of T by Tc to the power 3 by 2, okay. Now we have obtained actually the number of Bose particles, or you can say number of bosons in the system in the excited state at temperature T, okay. So if you want to find the number of particles of the Bose gas in ground state, that is if you want to find N0, what will be N0? N0 is, you know, simply equal to N minus Ne, okay, because N is the total number of particles. So N0, this is given as N minus Ne, okay. Now let us substitute the value of this Ne from this equation 1, and when you will substitute it, you can see we can take this N as a common factor, and this will be N times 1 minus T over Tc whole to the power 3 by 2, okay. So this is the number of Bose particles in the ground state, and you can see since T is less than Tc, T is less than Tc, so this T by Tc will be a number smaller than 1, and therefore this N0, which is number of particles in the ground state, this will have an appreciable value. So you can say that when temperature of the gas is less than critical temperature, then a large number of particles remain in the ground state, okay. And from here you can also see that if this T tends to 0, T tends to 0 Kelvin, it means the temperature of the gas is lowered almost equal to absolute 0 temperature. Then what will happen? If T becomes 0, this T by Tc will be 0, and this N0 will be almost equal to N, almost equal to N, or you can say that N0 tends towards N. So what will happen? It means in the 0 Kelvin range temperature, all particles of this Bose gas are found in the ground state. Since all the particles are in ground state, so they are governed by the same wave function, and such a state is actually called, or such phenomenon is actually called Bose-Einstein condensation. All these things you have discussed in the previous lecture in very detail, okay. So nothing in this discussion till now, nothing is new for you, but now after this you will learn something more about the thermodynamical behavior of this Bose gas under the condition T less than Tc. So you can see when T is less than Tc, actually in that condition the Bose gas is found in two phases. You can see all those things which I have just discussed is mentioned here. For your convenience, you can note down these facts in your notebook. Okay. And as I have told you that this T in the condition T less than Tc, this ideal Bose gas may exist in two phases. What is the first phase? In fact, there will be a gaseous phase constituting or consisting of this Ne particles distributed over the excited state. That is a state where E is not equal to 0. Okay? And apart from that, there will be a condensed phase, and that phase actually consists of N0 particles occupying the same energy state E equal to 0, which is called ground state. And actually this forms Bose-Einstein Condensate. Okay. So in these two phases the Bose gas exists when temperature is less than critical temperature. Now actually in this condition when T is less than Tc, now we are going to calculate the different thermodynamical properties of this ideal Bose gas. Starting from energy of the gas, we will try to find the different thermodynamic properties. Okay. Actually, see this figure. Actually, here I have plotted a graph of N0 by N and Ne by N in against of T by Tc. Okay. Actually, you can see this curve number 1 represents the graphical plot of N0 by N in against of T by Tc, and this curve number 2, this represents the curve for graphical plot of Ne by N in against of T by Tc. So you can see when corresponding to this point O, temperature is equal to 0 Kelvin, and when this temperature T will be 0 Kelvin, then what is the value of N0 by N from this graph? You can see N0 by N is equal to 1, which means N0 is equal to N. It means at absolute 0 temperature, all particles of this ideal Bose gas are in the ground state. And that is the famous phenomenon of Bose-Einstein condensation. Okay. On the other hand, you can see that at this temperature T equal to 0 Kelvin, this Ne over N, this is equal to 0 because this curve actually intersects the origin here. And so in this condition, Ne will be equal to 0. It means at 0 Kelvin temperature, no particle of this ideal Bose gas is present in the excited state. All particles are in the ground state. But you can see as the temperature T increases means T by Tc increases. See the graph. As T by Tc increases, you can see N0 by N decreases. N0 by N decreases. It means number of particles in ground state decreases. On the other hand, you can also see that this Ne by N increases. Ne by N increases. Okay. Ne by N increases. And see this figure. When T is equal to Tc, that is, you can say that T by Tc is equal to 1. This is shown in this figure here. Let us say this is a point P, and this represents the point where T is equal to Tc. And you can see this curve of N0 by N intersect this temperature axis here. So in fact, when T by Tc is equal to 1, then N0 by N, this is equal to 0, which means N0 is equal to 0. It means no particle is in the ground state at critical temperature. Okay? And since N0 is 0, so definitely you can say that this Ne will be equal to total number of particles. So at this temperature, all the particles of Bose gas are found in excited state. Okay? And we can also see that as T is greater than Tc, when T becomes greater than Tc, actually this is the region where T becomes greater than Tc, then only the gaseous phase exists which is in excited state. Okay? And at this point, let us say this is a point Q where these two curves intersect one another. Actually, at the point of intersection, the value of N0 and value of Ne both are equal. Okay? Both are equal. And this actually occurs at a temperature T by Tc equal to 0.63. 0.63. It means when temperature of the gas is 0.63 into critical temperature Tc, then the probability of finding this Bose particles in the ground state and also in the excited state are almost equal. Okay? So how this number in the ground state and in excited state varies with temperature, I think you have definitely understand. Okay? Now after this discussion, we are going to find the thermodynamical properties of this Bose gas at a temperature T which is less than Tc. Mark it. I am repeating these things here because we are considering the case when temperature of the gas is less than critical temperature. And the graphical discussion which I have just told to you, all those things here I have mentioned for your convenience, that at T equal to 0 Kelvin, all particles of the system occupy the ground state equal to 0, and at T equal to Tc, all the particles are in the excited state, and for T greater than Tc, we have gaseous phase alone. Okay? So I have mentioned these facts in brief here for your convenience. Now let us try to calculate the different thermodynamic properties of this ideal Bose gas under the condition T less or equal to Tc. So in this regard, first of all, we will see what will be the total energy of this ideal Bose gas at temperature T which is less than Tc. Okay? Actually, as you can see, we have mentioned earlier the previous result which we have obtained in the first lecture on this subject. Okay? So see this equation A2. Okay? Equation A2 defines the energy of this gas at any temperature T. Okay? At any temperature T. And this equation A4 defines the number of particles of this gas at this condition T equal to Tc. So if you want to relate the energy of the gas with critical temperature, you must divide equation A2 by A4. A2 by A4. See these two equations. Again, this is your equation A4 and this is your equation A2. Okay, have you seen it? And after seeing these two equations, when you will divide equation A2 by A4, then the result will be U divided by N, and that will be equal to, in fact, this much, 3 by 2 zeta 5 by 2 divided by zeta 3 by 2 kt times T over Tc to the power 3 by 2. This n is here actually. And so U will be equal to then this much into n. So you can say that at temperature T, the energy of this Bose gas is equal to 3 by 2 zeta 5 by 2 by zeta 3 by 2. These are Riemann zeta function, and you have learned about this in the previous lecture. nkt times this much. Okay. So here actually there is a product of T and T to the power 3 by 2. So this is actually T to the power 5 by 2. And except this temperature T, all other quantities are constant. So you can say that the energy of the gas at temperature T is proportional to T to the power 5 by 2. But they mark the restriction. This T cannot be and cannot have any value. This T must be less or equal to Tc. Only then this result will hold. Okay? Only then. Now, this zeta 5 by 2 and zeta 3 by 2, all these have standard values. So, you can find in terms of that standard value too. But before that, let us see what will be the energy of this gas at the transition point, or you can say at the critical temperature Tc. So, if you want to find the energy of this gas at critical temperature Tc, you should put T equal to Tc in this equation 3. So you can see when T will be equal to Tc, this T by Tc will be equal to 1, and here at the place of T we will substitute Tc. So U at T equal to Tc can be given as U at T equal to Tc. This is 3 by 2 zeta 5 by 2 divided by zeta 3 by 2 nk Tc. Okay. Now, when you will substitute the value of this zeta 5 by 2 and zeta 3 by 2, after simplification you will get 0.5134. You should remember this number, definitely. Okay. So, at critical temperature, the energy of this ideal Bose gas is given by 0.5134 times 3 by 2 nktc. Now, can you say that if your gas is a Boltzmann gas, that is a classical ideal gas, then what is the energy of the gas at temperature T? You know, in case of Boltzmann gas, the energy of the gas at temperature T is 3 by 2 nkt. You have learnt this in the lecture on Boltzmann statistics. Okay. So at temperature Tc, what will be the energy of the Boltzmann gas? That will be 3 by 2 nktc. Okay. So this is the energy of a Boltzmann gas at temperature Tc. And equation 4 defines the energy of an ideal Bose gas at same temperature Tc. You can mark the difference. In fact, this extra factor 0.5134 is here, and this is almost equal to 1 by 2. So you can say that the energy of an ideal gas at transition temperature Tc is about 1 by 2 times of that of an equivalent Boltzmann gas. Equivalent Boltzmann, because this number is just 1/2. Okay. So you can mark this difference, that at the same temperature the energy of Boltzmann gas and the energy of Bose gas are not same. If you are talking about the critical temperature, then the energy of Bose gas is almost half of the energy of Boltzmann gas. Okay. So I think you have clearly understand this. Okay. Now, after knowing the expression for energy of Bose gas, we can easily find the specific heat of this gas at constant volume. You know, this specific heat at constant volume Cv is defined like this. Cv at T equal to du by dt. Okay, and see what is the expression for this u. You can see here. This is your expression which I have defined in this equation 3. So, except this t to the power 5 by 2, here there is a product of t and t to the power 3 by 2. So, as a whole you can say that this is t to the power 5 by 2. So, except that t to the power 5 by 2, all other quantities are constant. So, when you will differentiate this u with respect to temperature T, what will be your result? You can see. This will be 3 by 2 zeta 5 by 2 over zeta 3 by 2 Nk divided by Tc to the power 3 by 2 and derivative of T to the power 5 by 2 with respect to T. So, this is d dt T to the power 5 by 2. Now, after differentiation of this, what will be your result? This will be 5 by 2 into T to the power 3 by 2. 5 by 2. Okay? And so, and here there is 3 by 2. So, this product will be what? This will be 15 by 4. Okay? And finally, you can say that Cv comes out to be 15 by 4. Sorry, this will be just okay. This is a regular feature of this device. So, don't worry. See here. So, Cv comes out 15 over 4 zeta 5 by 2 over zeta 3 by 2 Nk times T by Tc to the power 3 by 2. Okay? And when you will substitute the values of zeta 5 by 2, zeta 3 by 2 and simplify, your result will be finally Cv at temperature T equal to 1.926 times Nk times T over Tc to the power 3 by 2. So you can see that this Cv is proportional to 3 by 2. T to the power 3 by 2. Okay, T to the power 3 by 2. Okay, you can see that when you study the lattice specific heat capacity, that is device theory, then you see that in fact in case of crystal lattice Cv is proportional to T cube, but in case of this Bose-Einstein gas, that is Bose gas, Cv is proportional to 3/2 power of temperature. Okay. Now, after getting the value of Cv at temperature T, which is less than Tc, now we can easily find what will be the value of this Cv when temperature is equal to Tc. For this, we will simply substitute in this equation 5 Tc instead of T. So, when you will take Tc at the place of Tc, this T by Tc will be 1, and therefore, Cv at Tc is equal to 1.926 times Nk. 1.926.Nk. This is the value of a specific heat of this Bose gas at constant volume at critical temperature. Okay. So I hope you are clearly getting the things, because this is a very simple calculation, but something you have to remember, these numerical values you have to remember. Okay. Now let us find another very important property of this Bose gas, and this is actually entropy of this gas. You know that entropy is a very important thermodynamical property of any thermodynamical system. Now you know that entropy is always, in fact entropy is a state function, so always its change is defined. Okay, and for here for in this condition, we want to calculate the value of entropy at any temperature T. And for this, we consider a reference that when T is equal to 0 Kelvin, then entropy is equal to 0. And this is also called third law of thermodynamics. We consider this assumption. So you can see in this condition, if you consider that at T equal to 0 K, entropy is 0, then at any temperature T, entropy of this gas will be defined by integral 0 to T Cv divided by T dt. Okay, Cv by T dt. Okay, and now substitute this value of Cv from here, and you have to divide it by T. So in fact, after dividing by T in this expression, except this T, all other quantities are constant, and you can write it like this. This is 5 by 2 zeta 5 by 2 divided by zeta 3 by 2 and k, and integral of T to the power half, integral of T to the power half, and this will be actually equal to what? That will be in T to the power 3 by 2 divided by 3 by 2. And so when you will divide this 15 by 4 by 3 by 2, your result will be 5 by 2. Okay, and again we will have T to the power 3 by 2. So after integration, we will get that S is equal to 5 by 2 times zeta 5 by 2 by zeta 3 by 2 times nk T by Tc whole to the power 3 by 2. Okay. Now see the expression for the energy of this gas. This is the expression for energy, which is defined in this equation number 3. So if you will use this expression of energy in the expression of entropy, you can relate both of these quantities, and after using that result, you can easily see, I have not done the algebra here, you can easily done it, you can easily do it. So this is S equal to 5 by 3 U by T, U by T. Okay, this is actually the relation between S and U, you can also say. After knowing the value of entropy of this ideal Bose gas, now you can easily find what will be the Helmholtz free energy function. You know, Helmholtz free energy function A is defined by U minus Ts. This is just the basic definition of this free energy. Now, as you can see from here that this product S times T, this will be equal to what? This is 5 by 3U. This is 5 by 3U. Okay. So here I have written 5 by 3U at the place of this product Ts. Okay. So A is equal to U minus 5 by 3U, and therefore this A is equal to minus 2 by 3U. Okay. So we have also obtained this Helmholtz free energy of this ideal Bose gas in terms of energy of the gas. Okay. Finally, in last, we are going to calculate a very important property of this gas. This is actually pressure. Okay. In fact, when temperature T is less than Tc, then this pressure of the gas is given like this. This is kT divided by lambda cube zeta 5 by 2. Okay. And when you will substitute the value of this lambda, which I have defined earlier, which is called thermal de Broglie wavelength, and all the other constants, then your result will be 0.5134 nkt by V times T by Tc to the power 3 by 2. And so you can see here there is a product of T and T to the power 3 by 2, which is equal to T to the power 5 by 2. So you can see that this pressure of the gas is also proportional to T to the power 5 by 2, just like energy. Okay. Now, after getting the result for pressure at any temperature T which is less than Tc, we can easily find what will be the pressure of this Bose gas when its temperature is equal to critical temperature Tc. So you can see when T equal to Tc, then this ratio will be equal to 1, and so this last factor will be 1, and P will be equal to 0.5134 times nk Tc by V. Now T will be written Tc. So you can see I have mentioned it here that at critical temperature the pressure of this ideal Bose gas is given by 0.5134 nk Tc divided by V. Okay. Again you can see if you are talking about the Boltzmann gas, that is the classical ideal gas, then you know from equation of a state that PV is equal to nkt. So if you are talking about the critical temperature, then PV will be equal to nk Tc. Okay, and what will be then P? P will be nk Tc divided by V. Okay. Now compare this result and this result. Okay. You can see in case of ideal Boltzmann gas, the pressure at critical temperature is equal to nk Tc by V. But in case of ideal Bose gas, this pressure at critical temperature is equal to 0.5134 times nk Tc by V. So in fact this pressure in case of ideal Bose gas is almost half of the pressure in case of Boltzmann gas. Okay. So how the different property differs in case of Boltzmann gas and in case of this Bose gas, particularly at in the region of critical temperature, you have learnt in this lecture. Okay. So I have mentioned it here. You can see that the pressure of an ideal Bose gas at Tc is about 1/2 of that of an ideal Boltzmann gas. Okay. So these were the important thermodynamical properties of ideal Bose gas. So how they vary with temperature, what are their values when temperature is equal to critical temperature, all these things we have learnt in this lecture. Okay. I hope you have definitely enjoyed this lecture. Okay. Thank you very much.